Imagine waking up, you flip the light switch, and, well, nothing happens.
Just total darkness.
Right, and not because a tree fell on a power line down the street or, because of some rolling blackout during a summer heat wave.
Oh, this is much bigger than that.
Exactly. It's because for the last 3 years, the wind across your entire continent simply hasn't been blowing as hard as it usually does.
A multi-year energy drought.
Yeah, I mean, it sounds like the premise of a dystopian sci-fi novel, but it's actually the exact nightmare scenario that is keeping global energy planners awake at night.
It really is the ultimate bottleneck to a fully defossilized world. Because when you take fossil fuels out of the equation entirely, you are suddenly at the mercy of planetary weather patterns.
You're just waiting on the wind and the sun.
Right. And the problem is humanity tends to have a very, very short memory. We basically look at the past couple of decades of weather, we find the average, and then we build our systems to handle just that.
Which feels safe, I guess.
It feels clean, and it's mathematical. But as it turns out, it is incredibly dangerous.
And that false sense of security is exactly what we are tearing down today. Welcome to another deep dive. We are taking you into the absolute cutting edge of grid resilience.
And we have some really eye-opening data to get through.
We really do. We're looking at a fascinating new study, and I actually want to read the exact title for you because it sets the stage perfectly.
It's a bit of a mouthful.
It is, but here I go. It's called Interannual Electricity Balancing in 100% Renewable Energy Systems, assessed through a techno-economic comparison of data series length, e-hydrogen versus e-methane, and multi-objective solutions.
So the mission of this deep dive is to basically explore how current planners are drastically underestimating the chaos of the weather and why a highly surprising chemical actually beats hydrogen for saving our grid.
And we'll also get into how a clever mathematical trick can make this entire transition affordable.
Let's start with that short memory problem you mentioned.
Right. Because to solve the riddle of long-term energy storage, we first have to understand the true scale of the weather's variability.
You have to know what you're actually up against.
Exactly. And when I was reading this study, their critique of how we currently plan our power grids, it really struck a chord with me.
How so?
Well, think about it like packing for a vacation to a tropical island. Checking last week's weather doesn't help you at all if, a once-in-a-decade hurricane is brewing offshore.
Right, you need a much wider lens to see the actual threats.
Exactly. And this study points out a massive blind spot. Standard energy planning relies on just a 22-year weather data set from NASA.
Which is, 22 years is nothing on a planetary scale.
It's a blink of an eye.
It really is. When you only look at 2 decades of weather, you're looking at a smoothed-out version of reality. You capture the typical seasonal variations, summer to winter.
Sure.
But you are statistically guaranteed to miss what climatologists call high-impact, low-probability events, or HILP events.
That's basically the hurricanes in our packing analogy.
Exactly. Or in the energy sector, multi-year wind droughts. We're talking about prolonged periods of suppressed solar irradiation due to complex shifting climate oscillations.
Like El Nino and things like that.
Right. Or even massive volcanic eruptions that can literally dim the sky for years at a time.
Wow.
So to find these hidden monsters, the researchers didn't use that 22-year NASA data. They went much bigger. They simulated the entire global grid using the ERA5 dataset.
And how far back does that one go?
It goes all the way back to 1940. So that is 85 years of deep, chaotic weather variability.
Okay, so what actually happens when you plug 85 years of weather chaos into our current models? Like, does the math still hold up?
Oh, it shatters. It completely falls apart.
Really?
Yeah. Failing to account for those 85 years leads to a terrifying reality of underplanning. Because if you design a 100% renewable grid based on just 22 years of data, it might look perfectly cost-optimal on your spreadsheet.
Everything balances out on paper.
Right. But in the real world, when that inevitable multi-year energy drought hits, the grid simply fails. You physically will not have enough energy stored to bridge a gap that lasts for years.
So to fix that, to actually survive an 85-year weather cycle, we have to overbuild the grid, right? Like we need extra wind turbines and solar panels just sitting there for when things get bad.
Yes, intentional overcapacity. And the study gets incredibly specific about this penalty. I actually want to make sure I state their exact findings on this.
Go for it.
They report strictly on the cost-optimized case, noting that when compensating for interannual variation across the longer data set, the demand-weighted average overcapacity increases from 5.2% to 8.1% in percentage reference to the single-year case, without overcapacity to compensate for interannual variation.
Okay, wait, jumping from 5.2% to 8.1% might sound like a minor tweak on paper, just 3 percentage points.
But it's really not.
No, we need to visualize what that means in actual steel and silicon. We are talking about millions of additional solar panels, thousands upon thousands of massive offshore wind turbines built globally simply to act as a buffer.
It is a staggering amount of physical infrastructure.
And the financial side of that is just as heavy, because the study also strictly reports that the demand-weighted average total annualized cost markup increases from 2.9% to 4.5% in percentage reference to the single-year case without interannual storage or respective overcapacity.
So the premium society must pay to essentially ensure the grid against these high-impact weather anomalies. It almost doubles.
Which is why.
And that is just the true cost of robustness. Plus, keep in mind, those are just global averages. The burden isn't evenly distributed everywhere.
Oh, yeah. The regional extremes in this data blew my mind. Like the global average jump is one thing, but then you look at a place like Finland.
Finland is a brutal example.
It is. The study notes that in Finland, the required overcapacity leaps an astonishing 173% when you look at the longer 85-year weather history compared to the shorter one.
Just massive.
A 173% jump. Their weather variations over a near-century scale are just so extreme, it requires them to essentially build almost triple the backup infrastructure.
Which logically forces us into a massive engineering corner. I mean, if we establish that we absolutely must intentionally overbuild the global grid by over 8% just to survive a bad decade.
What happens during the good years?
Exactly. We are going to be generating a mind-boggling amount of excess power. Where on earth do we put hundreds of terawatt hours of electricity so it doesn't just go to waste?
And we cannot use lithium-ion batteries for that.
No, absolutely not. Those are fantastic for holding power for a few hours, maybe a few days. We need a battery that can hold power for 3 years.
Which brings us to the ultimate battery showdown. And honestly, here's where my expectations were totally upended.
Because of the hydrogen hype.
Yes. If you read any tech news, hydrogen is constantly hyped as the holy grail of clean energy. Like, the hydrogen economy is supposed to save us all.
Right. It's everywhere.
So shouldn't green hydrogen be the undisputed, obvious winner for storing this massive ocean of excess power?
Based on the headlines, you would absolutely think so. But the researchers tested 2 chemical energy carriers for this bulk storage.
Okay, what were they?
Electricity-based hydrogen, which we call e-hydrogen, and electricity-based methane, or e-methane.
Got it.
And the study reveals this brilliant paradox between thermodynamics and economics.
A paradox.
Yeah, because purely from a physics standpoint, e-hydrogen is the clear winner. It boasts a round-trip efficiency of about 33%.
Meaning, if I take 100 units of excess wind power, use it to split water and make green hydrogen, store it, and then burn it in a turbine 3 years later, I get 33 units of electricity back.
Correct. Now compare that to e-methane, which is noticeably less efficient. It sits at around a 27% round-trip efficiency.
And the reason for that efficiency drop is the extra manufacturing step, right?
Yes, exactly.
Because to make e-methane, you have to take that green hydrogen, then use huge direct air capture machines to suck carbon dioxide out of the atmosphere, and then mash the hydrogen and carbon together in a methanation reactor.
And that methanation process is highly exothermic, meaning a massive amount of your precious energy is just lost as heat.
So you're just burning off energy.
Right. So thermodynamically, methane is a worse battery. You have to build even more wind turbines and solar panels just to make up for that lost efficiency.
But didn't they find it's better anyway?
They did. What's fascinating here is that the study proves that despite this severe efficiency penalty, e-methane completely crushes hydrogen economically.
Okay, I need you to unpack the math there, because it wastes more energy and it forces us to build more solar panels to cut through the waste, but it is still cheaper.
Staggeringly cheaper.
Yeah.
Globally, opting for the e-methane pathway results in an annualized cost that is approximately 74% lower than relying on e-hydrogen.
Wait, a 74% discount? That's not just a competitive margin. That is a total landslide. How does throwing energy away save that much money?
The secret lies entirely underground.
Underground?
Yes, when you are storing hundreds of terawatt hours of energy, you cannot use steel tanks on the surface. There simply isn't enough space or honestly, enough steel in the world.
Oh, that makes sense.
So you have to pump the gas into massive geological formations deep within the Earth's crust.
Like salt caverns or empty oil fields, stuff like that.
Exactly.
Okay.
And here is the fatal flaw of hydrogen. It is the smallest molecule in the universe. It's essentially just a proton and an electron.
Okay, so it's tiny.
Because it's so tiny, it is an absolute nightmare to contain. It leaks through almost anything. And worse, it causes something called hydrogen embrittlement.
What is that?
Those tiny hydrogen atoms actually slip between the microscopic iron atoms in steel infrastructure, wedging them apart. Over time, it turns flexible, strong steel pipes into something that shatters like glass.
Oh, wow. So you can't just pump it into any old hole in the ground or use regular natural gas pipes?
No, not at all. You need highly specific, pristine geological salt caverns, which are geographically quite rare.
And if you don't have them?
If you don't have those, you have to excavate and build chemically lined rock caverns from scratch, which is just an engineering nightmare. The study puts the capital expenditure for hydrogen cavern storage at 1.03 euros per kilowatt hour.
And for methane?
0.23 euros per kilowatt hour.
That is a massive difference.
It really is.
Right.
Methane is a much larger, much more stable molecule. It doesn't embrittle steel. It can sit happily in vast, incredibly cheap, depleted natural gas fields that are already scattered all over the globe.
So the storage component for hydrogen is more than 4 times as expensive.
Yes. And when you are building a planetary-scale battery, that capital expenditure utterly dominates the map. It wipes out hydrogen's thermodynamic advantage completely.
So we basically just use the Earth itself as a giant, cheap methane battery.
Pretty much, yeah.
And it's not just the caves, is it? It's the plumbing, too. Because e-methane is chemically identical to the natural gas we use today, right?
Absolutely identical.
So that multi-trillion-euro global network of pipelines, compressors, and storage facilities we spent a century building, we can just keep using it. E-methane drops right in seamlessly.
Exactly. Whereas a hydrogen economy requires humanity to essentially build a brand new, highly specialized, multi-trillion euro pipeline network from scratch, because pure hydrogen will eventually destroy our current natural gas pipes.
It is such a wild concept to wrap your head around. We are going to use direct air capture to pull carbon out of the sky, mix it with hydrogen to make synthetic methane, pump it into empty gas walls for 3 years, and then pull it back out to burn it when the wind stops.
That's the plan.
And that whole convoluted heat-wasting process is still 74% cheaper than just storing the hydrogen.
It perfectly illustrates why energy planners have to model the entire macroeconomic system. You cannot just look at the physics of a single component in a vacuum.
Okay, but even with a massive 74% discount from choosing methane, we are still left with a pretty daunting reality here.
Yeah, it's not cheap.
Right. Building a planetary grid with enough extra capacity and underground storage to withstand an 85-year mega drought is going to cost an absolute fortune.
It is.
So how do actual societies afford this without crippling their economies?
Well, this is where the researchers introduce a brilliant conceptual tool they call the Tau analogy. It is a mathematical framework to find the ultimate policy sweet spot.
I found this part so fascinating. I was thinking about it like buying insurance for your home. You happily pay for insurance against a fire or, a tree falling on your roof.
Sure, standard risks.
But you wouldn't buy a multi-million-dollar policy to insure your house against an alien invasion or a meteor strike because the premium would cost more than the house itself.
Right, that would be absurd.
You have to find the sweet spot of maximum protection for a reasonable cost.
And the Tau analogy scales that exact insurance concept up to the macroeconomic level. When the researchers plotted out the cost of these grid systems against the amount of extra wind and solar capacity they built, they generated a Pareto curve.
Paint a picture of that curve for us. What does it actually look like?
Imagine a steep L-shaped graph. On the far left, you have a system where you build 0 extra wind and solar panels. You build exactly what you need for a perfectly average day.
Okay.
But to survive a multi-year drought with that bare minimum generation system, you have to build an astronomical, physics-defying amount of e-methane storage. The financial cost is sky high, way up on the top left of the L.
Right, because you're banking everything on the battery.
Exactly. Now, as you move to the right on the graph, you start intentionally overbuilding your generation. You build 1% more solar panels than you need, then 2% more, and so on.
And as you build more generation, you don't need as much storage.
Precisely.
Because your oversized solar arrays are catching whatever tiny scraps of sunlight are available, even during a historically bad year. You generate just enough to scrape by without needing to drain a massive battery.
And what the graph shows is that the total system cost drops incredibly steeply at first. Just a tiny bit of overcapacity slashes the need for massive storage.
But it doesn't keep dropping forever.
No. Eventually, as you follow the L shape, the curve flattens out into a long tail. You hit a wall of diminishing returns. Overbuilding by 20% doesn't save you much more money than overbuilding by 10%.
So where does this tau concept actually come in to solve the graph?
Well, the researchers borrowed tau from electrical engineering. Specifically, it's the time constant of a charging capacitor.
Oh, interesting.
Yeah, when you charge a capacitor, it fills up super fast at first, and then it slows down as it gets full. The tau point is a mathematical constant representing the exact moment it reaches 63.2% of its maximum charge.
So it's the mathematical point where you've gotten the absolute most bang for your buck before those diminishing returns take over.
Exactly. And they applied that 63.2% capacitor math to the Pareto curve to identify what they call the tau-1 solution.
Which does what?
It marks the exact percentage of overbuilding where a system achieves 63.2% of the total possible cost reduction. It completely takes the guesswork out of finding that economic sweet spot.
Okay, I mean, a math concept borrowed from circuit boards is great on a chalkboard, but I need real-world proof. Did they actually test if this saves money for a real country?
They did.
Because abstract math doesn't pour concrete or build solar panels, you know.
Oh, the study models real regions, and the results are profound. Let's look at the region of Java and Timor-Leste.
Okay.
If their policymakers tried to build a grid with the absolute bare minimal amount of renewable overcapacity, relying heavily on storage, their interannual storage cost markup would be a prohibitive 271%.
Wow. Meaning the methane battery alone would cost almost 3 times as much as the entire rest of the power grid combined.
Exactly. Totally unaffordable.
A complete political non-starter.
But by applying the tau analogy, the researchers found the sweet spot. If Java and Timor-Leste implement a tiny, modest 2% absolute increase in their renewable overcapacity.
Literally just building 2% more wind and solar farms.
Yes, that is their tau-1 solution.
Yeah.
And that tiny 2% addition slashes their storage cost markup by more than half, plummeting from 271% down to just 103%.
Oh, that is incredible. A fractional tweak to the amount of solar panels you put in a field completely halves the cost of the giant underground infrastructure.
It really is amazing. It proves mathematically that you do not need infinite, impossibly expensive storage, and you also do not need to blanket the entire country in redundant solar panels.
You just find the balance.
Right. If you strategically overbuild just a tiny bit of generation based on the tau-1 metric, you hit a sweet spot that makes a 100% renewable grid financially feasible for society.
This has been such a journey. Let's recap what we've unpacked for you today. First, we learned that true grid resilience is an illusion if you are only looking at the last couple of decades of weather.
22 years just doesn't cut it.
No, it doesn't. Surviving the future requires nearly a century of weather foresight, utilizing that 85-year ERA5 dataset to simulate those devastating, high-impact, low-probability droughts.
Second, in the battle of the TW8 scale batteries, e-methane is the surprising, undisputed financial champion over hydrogen.
Even though it wastes more energy.
Right. Thermodynamics takes a backseat to the reality of cheap, depleted underground gas fields and the multi-trillion-euro pipeline network we've already built.
And finally, the tau analogy gives policymakers a literal mathematical roadmap to afford it all, proving that a targeted tiny bit of overbuilding saves an astronomical amount of money on storage.
It is a remarkable piece of work that shifts the entire paradigm of how we should be modeling the energy transition.
The study, again, is called Interannual Electricity Balancing in 100% Renewable Energy Systems, assessed through a techno-economic comparison of data series length, e-hydrogen versus e-methane, and multi-objective solutions. It is a dense, deeply technical read, but the real-world implications are absolutely world-changing.
If I can leave you with one final thought to mull over.
Yeah.
We've spent this entire time talking of the absolute necessity of looking backward, right?
Right, checking the historical data.
This study proves that relying on just 22 years of historical weather data creates a dangerously fragile grid. But it relied on 85 years of past data to expose that fragility. So what happens when we fully realize that a changing climate means the next 85 years of weather won't behave anything like the last 85 years?
Oh, wow.
If past anomalies are our only benchmark, how do we build a grid for a rapidly shifting climate that has absolutely no historical precedent?
Oof. So that 85-year weather check might just be the baseline, not the ceiling. We're trying to pack for a hurricane, but we might actually be sailing into a completely uncharted ocean. Thanks for joining us on this deep dive. We'll see you next time.